Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 26, 2026, exactly 1 week ago. It challenges the standard scaling laws for large language models by introducing a geometric training objective that achieves baseline accuracy with 16 times less data. The paper is titled Semantic Tube Prediction: Beating LLM Data Efficiency with JEPA. And, as we'll see later, this method proves that principled geometric priors can outperform brute force scaling. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 captures the core intuition and the resulting performance boost. Panel A visualizes the semantic tube hypothesis, where the model's internal states are encouraged to follow a straight, smooth path called a geodesic. Any deviation perpendicular to this tube is treated as noise to be removed. Panel B then demonstrates the payoff, where the orange lines show the new method dramatically outperforming the standard baseline in blue. In fact, it matches the baseline's full accuracy while using only 1/16 of the training data. Well, Figure 2 illustrates the risk of mode collapse under standard training. We see two distinct trajectories, one for Jeff Hinton and one for the speaker, shown as orange curves. Both pass through the central blue polygon, representing the researcher token's Voronoi cell. Since standard training only requires landing somewhere in this cell, the paths can get dangerously close. The red dotted line shows the result. The IAM trajectory drifts and accidentally jumps onto the Nobel Prize track. This collision proves that simply predicting the right token isn't enough. The model must strictly maintain its semantic trajectory. So, Figure 4 examines the loss landscape to confirm whether standard training naturally discovers these smooth paths. The blue and green curves at the bottom represent the standard next token prediction loss. Both drop rapidly to 0, showing that adding the new regularizer doesn't hinder the model's ability to predict text. However, the purple line reveals a problem. It tracks the semantic tube loss during standard training and remains high and flat. This proves that standard models fail to minimize geometric noise on their own. In contrast, the orange line shows that explicitly training with the new objective successfully reduces this tube loss, smoothing the trajectory while maintaining accuracy. Alright, moving from theory to practice, Figure 5 demonstrates how this geometric regularization translates into raw accuracy. The charts compare standard fine-tuning in blue against the new semantic tube approach in orange. Panel A shows consistent gains across diverse datasets, with particularly large jumps on synthetic tasks. Panel B proves this applies broadly, as the orange bars lead across families like JEPA and OpenELM. Finally, Panel C confirms scalability, maintaining a significant advantage even as model size increases to 8 billion parameters. While Figure 5 confirmed the broad success, Figure 8 now digs into the design choices with an ablation study. The orange bars on the left represent the semantic tube method, which clearly towers over alternative strategies like the green two-view approach or the blue masking techniques. Crucially, the authors found that simpler is better. For example, the third bar in the orange cluster, representing the PRED variant, shows that adding a learned projector actually degrades performance compared to the core method. This confirms that the direct geometric constraint is the most effective way to train. So, having established the best design, Table 2 lists the optimal settings for the single hyperparameter, lambda. Across most datasets like Synth and Spider, the ideal value consistently falls within a narrow range between 0.01 and 0.08. This stability holds true even for different model families in the middle row, such as Gemma 2 and Qwen 3. Interestingly, the bottom row suggests that as we scale up to larger models like Llama 3.8b, the optimal lambda decreases slightly to around 0.002. Wrapping up, the key takeaway is that geometry matters. By constraining models to follow smooth semantic tubes, this method matches standard performance with 16 times less data. This proves that smart geometric priors can break the brute force scaling laws we often assume are fixed. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.